Tish, I'm still picking up from your microphone.
I have a thing on.
I always mute her in the end. Okay, I'm going to say thank you very much, Riker, for being so brave as to have a go at doing this. This is a great experiment for Takura to see if we can see how well we can assess this. I better just flick the mark schedule to Tish as well. I'll flick it to you in just a second. So Riker and I've gone through roughly through the things he's going to talk about, but I'll leave it to him. So the idea is that we ask him questions which will help him to demonstrate the depth and comprehensiveness of his understanding, which is going to be at Curriculum 8, and he'll be able to make complex links between important concepts, and then we can give him excellence. And are you all ready? Have you got any questions, Riker, before we get going?
Yeah, just got a little bit of recording jitters.
Yep, so the red button's on, we're recording, so I'll hand over to you.
Okay, so the topic of my presentation is how stars are born, which is quite a complex subject. I'll be talking about these topics, and let's get started. So, stars form in dense clouds of gas called stellar nurseries, and they're mostly made of molecular hydrogen with trace amounts of other chemicals. And stars form when the denser regions of the cloud break off into clumps, and then these clumps of gas then collapse to form protostars, which are early stars before nuclear fusion starts. They're essentially large balls of plasma. And I see Seamus has a question. The dust clumps together because it's gravitationally attracted to all of the other particles in the cloud, so they're just, all of the dust particles are attracted to each other and they collapse down. And what causes the cloud to fragment, I'm not entirely sure. I remember reading something about different external phenomena like supernova. They can cause the cloud to break up. So does that answer your question? Okay, and moving on to the next slide. So when the gas cloud collapses, the clumps, when they collapse, if they're spinning even slightly when they collapse to form a protostar, then because of the conservation of angular momentum, they'll speed up, as shown by the relative sizes of the arrows and the clouds. So when it shrinks, it speeds up. For example, when you have a clump of gas which is about 0.1 parsecs in diameter, to give a bit of scale, that's about the size of the solar system. When a cloud of that size, with a mass of 3 solar masses, which is 3 times the mass of the Sun, collapses down to a protostar with the diameter of 3 solar diameters, then if you just go through the calculations, you can see that it has this particular angular momentum, and when you plug that back into a rearranged form of the equation, to find out what the final velocity is in terms of the initial velocity, you find that the final velocity is 740,000 times faster than the original cloud. So that's going to be quite a dramatic increase in rotational speed. Oh, hold on, I'm getting a little bit of buggy bits. Working on a small screen, so it's hard to hit the right buttons. Sorry about that. How does the rotational momentum relate to the start of a fusion reaction? Well, when the cloud collapses, the gravitational potential energy of the cloud, of all of the particles in the cloud, is turned into heat by friction, and that heats up the cloud, and that heat is what starts fusion. Did that answer the question? Okay, so when the cloud does collapse and heat up because of friction, then that slows down the collapse a bit, and the cloud will continue to collapse until hydrostatic equilibrium is reached. And hydrostatic equilibrium is when the force due to gravity is balanced by the pressure from within the protostar. And then when the star collapses, not all of the when the gas cloud collapses, not all of the gas cloud is turned into the protostar, and you end up with a ring of material around the outside of the star, along perpendicular to its axis of rotation. And these disks are called accretion disks. And material from the disk is attracted towards the protostar via gravitational and electromagnetic fields. And this increases the protostar's mass, which increases its rotational inertia, and again, by the conservation of angular momentum, that will slow down. So eventually the protostar will become large and hot enough for nuclear fusion to occur. And the gene's mass is the mass of the protostar when hydrostatic equilibrium is reached, and it's given by this rather complicated equation derived by Sir Jeans, and I'm not exactly sure how he derived it. I know that it was done by assuming a perfectly spherical ball of gas with gravity acting on it and pressure from within pushing outwards, and using the equation you can calculate the mass, you can calculate the temperature or the density for the star of a given mass to be stable. And yes, it does. Yes. Yeah, it is. Um, Jupiter could actually be considered somewhat of a failed protostar because it didn't actually turn into a plasma and gain enough mass to turn into a star. It's only for stars. I I'm pretty sure it's only for stars. So yeah, yes. Yeah, K is the Boltzmann constant, which is that's the same as when we take R, the oh I've got it in black. No, R the gas constant, and you divide it by Avogadro's constant. Yeah, sorry, that's supposed to be an A. Um, it looks more like a lambda. I suspect so. I only had this morning to read over it, so I'm not completely solid on it. So, hydrostatic equilibrium is when the gravitational force is balanced by the pressure force pushing outwards, and this happens when gravity can't collapse the star any further. And there is an equation for it which uses quite a little bit of like basic calculus to derive, and I like to go through how that's derived, if that's okay. There's no net force on the star from within, but there might be gravitational forces from other stars. So, with the equation for hydrostatic equilibrium, we're looking for an expression for how the pressure changes as the star's radius changes, and from that you can integrate to find an expression for the pressure at any point within a star. And I'm just going to swap over to a whiteboard. Okay. So imagine you've got a star like this. That, and it centers right there. Then you take a section. Oh, that wasn't supposed to happen. Just getting used to using the tools. Take a section out of the middle, like that, and in this tiny section right there, we are going to take a cylinder out of the surface of the star, just to just as a nice way of representing this area in here, the blue area. And so that cylinder looks like this. Excuse the badly drawn cylinder. And so that cylinder, we've got the star with radius r, and then we're just going to label the height of the cylinder as dr, so a small change in r, like an infinitesimally small change in r that you can't really count. And then the area of the top we're going to label as dA. And so just ignore the blue bit for now, and we'll treat this cylinder taken from the blue section as though it were an object sitting on top of this white section of radius r. So the gravitational force on the cylinder would be and so that force is acting from right there downwards. So then we can find out what each of these, m is, well, m is, it would probably be better to define m as a function m of r, which is just the mass of the star at that radius r. So like the mass that that sphere of radius r encloses. And then the mass of the cylinder we can define in terms of the density of the star at that particular point right there. So density, rho, is mass over volume. But what's volume in terms of this cylinder? It's just dA dr, the product of the two. So mass is, density is mass over dA dr. Which rearranges to give mass is, that should be a function, because you don't want to assume that the density of the star is constant throughout, because in a fluid the heavier particles would sink to the bottom. So if you have heavier elements such as hydrogen-2, deuterium, which is a heavier isotope of hydrogen, that would sink closer to the core of the star, and when it gets later into its life cycle, it would start fusing lithium, beryllium, carbon, so on. And so you'd end up with the elements ordered from heaviest at the center to lightest at the outside. It's like when you take when you take oil and water and you mix them together, the oil is less dense than water, so it floats on the top. So the less dense elements will be closer to the surface of the star. and so that's why you've got that function rho of r. So the density at that particular point r. And so if you substitute this back into this original equation for the gravitational force, which would be acting on this top surface of it would be acting from the center of mass of the cylinder. Just ignore that line, and so you end up with the force is equal to universal gravitational constant times the function m of r times m. Actually, it would probably be better to just substitute it in directly. So we select that and you substitute in m, so you get rho. Oh, I forgot to select the pen. Substitute in rho of r over r squared dr dA. So now we get to thinking about what the pressure force is from the cylinder. So the pressure at the bottom, let's just call that P of R. So what would the pressure at the top of the cylinder be? Well, it would just be P of R plus dr. But because dr is infinitesimally small, you can say that the change in P between there and there is equal to just P of R. So you get dP equals P of R. And then, so going back to the equation for pressure, pressure is just a force acting over an area. And that area is dA. And that should be P of R. So it's the pressure at that particular point. So you can rearrange that to get, let's just label that F of G, and then F of P for pressure force. So F of P is PR, which is the same as dP, dA. And so these two forces have to be equal in order for hydrostatic equilibrium to occur. I'll just clear the whiteboard to make this easier to... How do you clear the whiteboard?
I'll wait for my
Riker?
mute to turn off. Stop muting.
Just
Oh,
trying to
come
clear
on.
up a little bit of space. Also, there's a couple of buggy stuff with my full screen function on the computer.
Come on. Stop doing this to me, stupid thing. Sorry, what, did you just want another page?
Yeah,
Because you can just use the little tab at the bottom.
Oh,
So you
I
can just
didn't know that.
use the arrow thing and it'll give you
Oh,
another page.
okay, so there's
I
another
think.
page,
Should do.
and back to what we were doing.
It's not going there for me, I don't know why.
The two forces
You've gone to a new page. Do you want to go? Anyway, you can toggle backwards and forwards using the arrows at the bottom, Riker.
So the two
There you go.
forces, F of G, right there, that has to be equal to the pressure force in order for it to be balanced. Because the pressure force is acting upwards at the bottom of the cylinder, right there. So they have to be equal at that particular point, right there, at radius r. This is assuming that the pressure is constant at a particular radius, which, because of convection currents, there's small variances. So we get F of P equals G.
Yep.
And going back, we've got dP dA equals G M of R rho of R over R squared dR and so the dA's cancel out and you're left with dP. Something's wrong.
That's all right. We know what that reads. That
dP
says.
equals G of R rho of R squared dr, and then if you divide both sides by dr, you get the final expression dp dr equals G M of R rho of R over, that's the final formula.
So what's that telling us?
That's telling you that the rate with the pressure changes as you change the radius, so that's dpdr, is dependent on the density at that particular radius, the mass enclosed at that particular radius, and the radius itself. And if you want a function for the pressure at any particular point inside the star, you can integrate to get P equals D M of R rho of R over R squared dr. And the reason why I've just left M of R and rho of R as functions is because they're actually rather complicated functions that I don't fully understand. It's a lot of complicated stuff with fluid dynamics. And so
on Tish is typing, we'll wait for her. Fair enough.
But it is possible to get that as a final formula. It's just dependent on the particular star.
So can you explain how the density varies with radius in a protostar?
Well, the density would be higher at the center because you've got the more dense elements at the center. it's the they're more dense, so they sink to the bottom. It's like in like I was saying earlier, it's like when you mix water and oil, the oil is less dense, so it floats on the top.
Yeah.
And going back to the presentation. Exactly. So where were we? So we just did that, and then nuclear fusion. So after the stars reached hydrostatic equilibrium, and its core temperature is hot enough, or it's dense enough, then the ionized hydrogen nuclei begin to fuse. And why ionized? Because the protostar is a plasma, it's hot, and it has enough energy for the electrons to escape completely from the atom.
Yep.
And this process is called the proton-proton chain reaction. And a high temperature is needed to overcome the electromagnetic repulsion between the protons. They're both positively charged, so they repel each other, and if they collide with high enough energy, then the nuclear forces will take over, and they'll start to fuse. So you've got the three main reactions over here, where you've got two protons colliding, and you produce a helium nucleus, which has only two protons, no neutrons, and that's quite unstable. It immediately undergoes beta decay.
And that's
Positive
beta
decay.
positive decay, isn't it?
Yeah.
So it's emitting a positron.
Yeah. And then take the deuterium, which is produced from that reaction, and that reacts again with the proton to produce...
That's another proton, presumably.
Yeah, another proton. And it produces a helium nucleus with one neutron and a gamma ray. And there's no decay going on there because you can see that the mass numbers add up and also the charge numbers add up. So mass is conserved and charge is conserved as well. Then for the third step, you're taking two of the helium-3 and they fuse to produce helium-4 and two more protons which go back to fuel the first step. How do two protons form a neutron? If you go to the whiteboard, protons are made up of quarks, and so are neutrons. So a proton is made of two up quarks and a down quark. And a neutron is made of one up quark and two down quarks. So what happens is an up quark changes into a down quark, and in doing so there's an energy change because there's a difference in mass. So if the mass changes, then there's going to be energy released. Like if the mass decreases, there's energy released. And the gamma radiation is from a different step. That's when you have the positron. Well, it's in two steps. When you've got the positron reacting with free electrons inside the plasma, and there's also the other step which released gamma rays. But this particular reaction releases neutrino. That's a neutrino. Sorry, I'm getting my standard model mixed up.
You're doing very well. I think most physics teachers would be flummoxed with this question, so you're doing really well.
And it also releases a positron. So this is the overall Feynman diagram for that reaction. We've got space along there and time along there. So going back to the presentation, oh yeah, think got right here. So Seamus, like you were saying, gamma rays are produced in step 2, and they're also produced when you've got the positron reacting with an electron inside the plasma to produce 2 gamma rays. And so how can you apply all of this? Well, nuclear fusion reactors. The mass of hydrogen inside the reactor is far too small for gravity to compress it down and establish hydrostatic equilibrium and start fusion. So to compensate, you keep the hydrogen inside an electromagnet and you heat it up to extremely high temperatures. And if you go back to talking about the gene's mass right here, if you increase the temperature, then the gene's mass increases, and what this means is that you can effectively fuse a greater mass of hydrogen, or you can fuse a smaller mass more easily. And so they're raising the temperature up to compensate for the fact that the density isn't particularly high. So the density is N. And the gas is heated in 3 ways: by inducing a current in it, injecting high-speed jets of hydrogen, and radio frequency heating, which is exactly the same as in microwave ovens, where you have where you send electromagnetic waves into the plasma, and that excites the nuclei and causes them to move faster, so it heats them up. And most nuclear fusion reactors use heavier isotopes of hydrogen because the first step in the proton-proton chain reaction requires a lot more energy than the other 2 steps. So if you go back here, that step 1 requires quite a bit of energy, and step 2, fusing deuterium, which is the 21H, that's heavy hydrogen. When you fuse that with normal hydrogen, that requires less energy than the first step. So in most nuclear fusion reactors, they cut out the first step to make it more plausible. Any questions?
Can you just tell us why you chose that topic, Riker?
I'm not sure. I think it was something. I think I chose it because it was something that lets me do modern physics and mechanics at the same time, and it's hard to find topics that include both.
Yeah.
And I would have done just modern physics if I could, but I think it's good to include mechanics as well to get more of a rounded demonstration of my understanding.
Yeah. Any questions from anyone else?
Yeah, Riker, can you hear me?
Yes?
How difficult did you find? Can you sound good? Sound
Yep, yeah, I can hear you.
I can hear you.
Okay. How difficult did you find finding the resources? There's a lot of material on the internet, I know.
I mostly spent a lot of time looking through web pages for past university courses. So a lot of these you can see that they've got labels like Astrophysics 162 or Natural Science 102 from various different universities, and I used those materials to help find the information. So it was mostly a process of just typing everything into Google.
Yep.
No problem, Seamus. Glad you liked it.
Anything from guest? Not sure who guest is. Cool, I'll stop the recording.